Let's review the metric units. So if we want to measure length, we use, if it's just a basic unit with no prefix on it, that's just meters. If we want mass, we use grams. If we want volume, liters, yep, liters. And we'll talk about temperature in the next chapter. We're going to focus on just these for right now. So as you hopefully have heard before, the way the metric system works is you have your basic unit like meters, grams, or liters, and then you can put prefixes on them to talk about multiples of 10 or 100 or 1,000. So for instance, the way that that works is 1 meter is the same as 1,000 millimeters. So if we take a meter stick, we can call this 1 meter, or we can call it 1,000 millimeters, which are these tiny little lines. 1,000 is in there. And this is, in general, given by this prefix milli. We can think of milli as a fraction of 1,000th of something. And so that means that it works for every other unit. So 1 gram is 1,000 milligrams. 1 liter is 1,000 milliliters, and so on. So any unit you can come up with, you can have milli of that, which tells you a 1,000th of it. So there would be 1,000 of them in that. So we can write these equivalents, and we're just going to stick with that one for now before we look at some other prefixes and talk about how we express units in these different forms. So let's say we made a measurement with our meter stick that came out to 0.50 meters. Pen's being a little weird here. So let's say that's some measurement that we took. So let's say we want to express that in millimeters. You might be able to figure that out just by looking at it, but it's going to get more complicated, so let's do this whole process out. So there's a way that you can use equalities like what we wrote down up there to figure out how many of a particular unit is in another unit. And the way that you do this is you think of this as, rather than as an equality, like where things are on opposite sides of an equal sign, you think of it like a fraction. So that means we put one on top of the other. So let's take our meter one. 1 meter divided by 1,000 millimeters. So any math folks in the room, why does that work? You know, why can you take two things that are equal on two sides of an equal sign and just make a fraction out of them without changing what it is? What does that fraction mean? It's okay if you don't know this. We're really just saying that that fraction is equal to 1. So if two things are equal and you divide them by each other, you get 1. Like if you wrote down 2 equals 2, and then you took 2 divided by 2, you just get 1. So any two things that are equal, you can divide them and get 1. And that means that it's also equal to 1 if we were to flip those two. So if we were to put those millimeters on top and the meter on the bottom, that is still all equal to the same stuff. Because of this equivalence right here. So if you know that two things are equal, you can make a fraction out of them that equals 1. And it doesn't matter if you make that fraction with one on top or the other on top. It's the same thing. All right. So now we've got that equality. Well, how does that help us? It helps us because we can always, another rule of math is you can always multiply things by 1 and get the same thing. Have you heard that before, the identity idea? You multiply a number by 1, you get the same number back. So we can take our 0.5 meters and multiply it by 1 and still have 0.5 meters. That's not super helpful. But what if we use one of these other versions of 1 that we just wrote down? That can be more helpful. So what we can do is we can multiply this by one of those factors that we just wrote down. And I'm going to show you how to pick which one, but we're just going to do it first so you can see what that looks like. We're going to use that second one that we wrote down. And the reason we can do that, or the reason that we will do that, is, again, anything divided by itself is 1. So what this is showing is, first we're multiplying 0.5 by 1, which means nothing's happening to it. We're also multiplying, or we're also dividing meters over here by meters over here. Meters divided by meters, again, those are the same thing, so we can say that those cancel, that they equal 1. And in doing so, we're left with millimeters. So by evaluating this expression where we would say 0.5 times 1,000, we actually come up with the correct answer, which is 500 millimeters. So 0.5 times 1,000 is 500. Now, you don't have to go through that whole process every time you want to do this. I just wanted to show you how and why it works. If we think of it more from a functional standpoint, like how do you use this information, all you need to know is take the number that you want to change, multiply it by a conversion factor. So these things we're going to call conversion factors. You can multiply it by whatever conversion factor you want to. And we want to make sure that the unit that we are trying to get rid of, the unit that we're changing, in this case meters, that it's always on the opposite side in the conversion factor. So if it starts on the top, or just as a regular number, then we want to put the conversion factor on the bottom. So let's practice this and see how this works in some other situations. All right, so now instead of 0.5 meters, I'm going to take, we'll take a less friendly number, 472 millimeters. And let's say we want to convert that unit into meters. So how do we convert 472 millimeters to meters? First thing that I always think is helpful, especially when we get into more of like the story problem version of this, which we're going to look at in a minute, some minutes, is good to just write down what you're trying to do. So in this case, we're going from millimeters to meters. That's our goal here. We're changing from millimeters to meters. So we want to pick a conversion factor that can do that. We've got two we could pick from because there are two conversion factors that relate millimeters and meters. Which one are we going to use? The one on the left or the one on the right? Yeah, the one on the left. Why? Okay, yeah, go ahead. Yeah, we want the units to cancel out and give us new units. We want the units to be on the opposite sides. Another part of that I should specify, when we write down a number like we did here, 472 millimeters, another way to express that is to divide it by 1. Because anything divided by 1 is just itself. So when we're talking about things on the top versus the bottom, if you just write a plain number with nothing else around it that's not part of a fraction, you're assuming that that number is on the top. Because 1 divided by 472 is not the same. That's a very small number. But 472 divided by 1 is the same as 472. So we can take that and we can multiply it by this conversion factor on the left. And what I do with these to keep track of them is I always write down the units first and the numbers last. So all we need to know is what we wrote down in green over there, that we want to go millimeters to meters. And that tells us that we need a factor that has millimeters on the bottom to cancel out with the other one, and meters on the top. Then we can go back and fill in the numbers. So then we can go back and say, I know it's 1,000, but I can't remember. Is it 1,000 meters per millimeter, or is it 1,000 millimeters per meter? So we could look back at our equality and say, oh, okay, it's 1,000 millimeters per meter. So the 1,000 goes with the millimeters, and the 1 goes with the meters. If you notice what I just said, that's another way of keeping it straight too, is to have a sense of how big these things are. If you remember that this is a meter, and this little thing is a millimeter, the millimeters are little, however you want to remember that, then you can think about that. And when you're in kind of that high stress situation of a test or something, and you think, okay, I don't remember, does the 1,000 go on top or on the bottom? You say it to yourself in a sentence. There's 1,000 millimeters in a meter. Does that make sense? There's 1,000 meters in a millimeter. Does that make sense? So if you know that one is bigger than the other, you know there's going to be more of the little one in the big one. So the 1,000 millimeters in a meter makes sense. The 1,000 meters in a millimeter doesn't make sense. So that can be a way to help keep it straight. And the reason I'm spending so much time on that is that's the #1 problem in these. People tend to remember the numbers fine, the 1,000, whatever. It's putting them on the bottom versus the top. That's what gets turned around. So if you go units first and then match up the numbers, that gives you the best chance of not getting those flipped around. And it happens. I mean, you'll see me flip the numbers around for sure. But the goal is to practice enough and get used to this enough that it doesn't happen over and over again when it's important. All right, so to evaluate something like this, we multiply by the tops. All the things on the top get multiplied together, and then we divide by everything on the bottom. That's what the fraction line tells us. So in this case, we would say 472 times 1 is 472, and we divide that by 1 times 1,000, or we can just ignore the ones and say this is going to be 472 divided by 1,000. So if we do that calculation, we get 0.472 meters. Okay, and we've converted millimeters to meters. With me so far? All right. Now, have other people done this where you just move the decimal place? Is that how you've been taught before? Okay, so why are we going through all of this nonsense if we can just move the decimal place one way or the other? We'll get to that. The idea is this works for anything, for any crazy units, for going from feet to meters, for whatever kind of conversion you want. When we get into moles and all this special chemistry stuff, this technique still works exactly the same way. So if we can get this technique down, we can apply it to everything. And then when we are dealing with the metric system, if you want to just move decimal places, that's great. Then you can do that. But the procedure is really important for when we get to some more complicated stuff. So that's why we're doing it this way. All right. So now using those conversions we saw before, I'm just going to write down a couple and let you give them a try, and then we'll look at them together. So if you could convert 1.62 grams to milligrams, and 43.2 milliliters to liters. So if you're new to this, go through the way that we just talked about it. If you're not new to this and you want to just move the decimal place, go for it. But then I would also just try this, because we're going to use it later with more complicated stuff. Try this method and make sure you get the same number that you did when you were just moving the decimal place. Just to make sure it's all consistent. Yeah.
That's 432.
No, that is 43.2. Sorry. For some reason, this pen isn't making little dots nicely today. There might be something on there. I'm not sure. There's supposed to be a dot there. Everything that's up here will be posted on Blackboard along with the recording of it, so you can go back to it. Or if you feel like it's going too fast and you can't write, you just want to listen, it'll all be there for you. It's like most people are finished up. Let's be another minute. All right, let's take a look at these. So I didn't tell you specifically how to make conversion factors for grams and liters and milligrams and milliliters. Did anybody have trouble finding out how to do that? Because it works the same, right? So you could really use the same thing. And that's the neat thing about these metric prefixes is once you know them, then it always works the same regardless of what kind of a unit you're talking about, whether it's grams or liters or temperature stuff is a little different, but the other ones all work out the same way. So once again, we're looking at grams to milliliters. So we want to write that plan out that we're going to be, or grams to milligrams, sorry, grams to milligrams. Later, we're going to do some that are multi-step, so we have to go from one unit to another and then to another one. So we set this up with our conversion factors. So we need to find a conversion factor. This is one that we know because there's always 1,000 milli something in a gram. So we can write down a conversion factor as 1,000 milligrams in a gram. I think I'm going to have to restart the computer later, but it's all right for now. So there's 1,000 milligrams in a gram. We can use that conversion factor. So we can set that up to be 1.62 grams. And then we want grams on the bottom and milligrams on top because we started with grams. That's what we want to cancel. So we put that on the opposite side. And then we fill in the numbers, 1,000 milligrams in a gram. And so that tells us 1,620 milligrams. All right. Questions on that one?
You know, I just put a 0 at the end.
Yep.
I get confused with what was on top, what was on bottom.
Okay.
I was looking over right here.
That's great. So that's awesome. And yeah, if you just can move the decimal place and put the 0, that's fine. When we get into other units, we'll have to revisit that because we have to make sure that it's still okay. Okay. All right, so then the other one works the same way. We go milliliters to liters. So 43.2 milliliters. Our conversion factor, we want milliliters on the bottom and liters on top. So we always want the opposite unit right next to what we're dealing with. So if we want to go from milliliters to liters, we want milliliters and liters on the same side, and we want the other milliliters one to cancel, to be on the bottom. So then we fill in our 1,000 milliliters per liter, divide that by 1,000, and that gets us 0.0432 liters. Questions about those? All right, so that's how metric conversions work. Pretty straightforward, and as we said, you can just kind of move the decimal place around if you're comfortable with that. The ones that you need to know for this class are listed here. So kilo, centi, and milli. We talked about milli. Let's look at the other two and write them down up here just so you have them in the right place. We don't really have room. We'll just do them down here. So that prefix centi is C, and that's a 100th, which means there's 100 centimeters in a meter. All still works the same way, but we're using 100 instead of 1,000. So there's 100 centimeters in that meter stick. It also means that we can say that there are 10 millimeters in 1 centimeter. We did some of this when you're measuring on last Wednesday. The larger lines in the ruler are the centimeters, the smaller ones are the millimeters. So that's another conversion factor that we should know, that there's a 10 milli-somethings in a centi-something. Kilo, K, is a little bit different because it's larger. So rather than being a fraction of that regular unit, it's actually more of that regular unit. It's 1,000 of them. So there are 1,000 meters in 1 kilometer or kilometer. I don't know why I wrote out the whole word there. Let's just make a km. Similarly, 1,000 grams in a kilogram, 1,000 liters in a kiloliter. You could use that for any of those units as well. Okay, so those are the 3 units that you should know. You should know milli, centi, and kilo, and how to use them and convert between them. The more practice you get at those, the easier and quicker it'll be. You want to get to the point where you can pretty much look at a number and be able to convert within that system. Because it's just a matter of dividing and multiplying by 10, adding or getting rid of zeros, if you get enough practice at it, it starts to get pretty easy. But if you don't ever feel that comfortable with it, that's fine, because you can always go back and do it systematically with this procedure. It'll still work. Just look at the right answer. So let's move on and talk about what happens when the units aren't so nice and they aren't just hundreds and tens and thousands, but they're other kinds of numbers. So we'll say converting between systems. Let's use a problem from the book for practice here. let's try this one. A container holds 0.500 quarts of liquid. How many milliliters does it hold? So you got half a quart of liquid. How many milliliters does it hold? There's another word for half a quart. I think is a pint, right? Is that right? Anybody know? Anyway, these are the kinds of things you don't have to remember because we looked them up. So I don't expect you to know the conversion between quarts and milliliters. So we would look that up. We could look it up in the back of the book. If it were on a test or an exam or something, it would be given. Let's see if it's in here. It is. So we open the back of the book, and we find that it says right here, 1 quart equals 946 milliliters. Okay. So we have that equality. How do we use that to convert from 0.5 quarts? So what would you do? What did you do first?
You would write down that you're converting
Sorry. Okay, go ahead.
quarts to milliliters.
Yes. So let's say, okay, we know here that we want to go from quarts to milliliters. Now, luckily, we have that exact equality. We're going to look at some in a little bit where we don't. So we might have to go like from quarts. Maybe we didn't have quarts to milliliters, but we had quarts to gallons. So we could go quarts to gallons and gallons to milliliters or something like that. We'll get into those later. But, okay, great. So we've got our conversion factor. So now we can set up our problem the way that we did before. So we're going to put that first number down here, 0.500 quarts. And we're going to multiply it by a factor that allows us to convert quarts to milliliters. So what do we want on the top? What do we want on the bottom? Milliliters on the top and quarts on the bottom. How did you know that?
Because quart is on the top.
Yeah, the number that we started with is considered the top. So we want its counterpart here to be on the bottom so that those two can cancel each other out and we're left with milliliters. So now we need to fill in the numbers. How do we fill in the numbers? Which number goes with which unit? The 946 goes on top? That's right. So we keep it matched up exactly the same way it is in the equality here. So the 946 is with the milliliters here, stays with the milliliters here. Okay. Now we evaluate it. To evaluate this, we need to multiply by everything on the top, divide by everything on the bottom. We can ignore all the ones. So that means that we can just say 0.5 times 946. $473. All right, so half a quart is 473 milliliters. Okay, let's try another one. Should I close my book? Right, just because that number happened to be nice and happened to be 0.5. So this one says, what is the mass in kilograms of a person who weighs 145 pounds? So just because, let's try something a little bit different. So we start out the same way. Which unit are we starting with? Which unit are we going to, based on that question? Yeah, pounds to grams. So we're going pounds to grams. Whoops, not grams, kilograms, right? Kilograms. All right, so let's say we flip this, and you may even know this conversion factor, but let's say we flip back here to the book, and it's not there. It is there, but let's say it's not there. But let's say instead we find this one. So we don't find an equality that relates pounds and kilograms, but we do find an equality that relates pounds and grams, because we figure that's close, so maybe we can use that. Is there a way we can use that? How? Yeah, so we know that we can convert between grams and kilograms. So we can maybe change our path here a little bit. Instead of going from pounds to kilograms, we can recognize that we can get grams from kilograms, or kilograms from grams, and so we can use that pounds and grams equality right there. So rather than being able to take the direct route, we have to take an extra step to get there. So we have to go pounds to grams to kilograms. All right. So before I talk about how to set this up, give it a try. See if you can use the same techniques to set up the same kind of equation, but there's going to be an extra factor in there this time because of that extra step. Just kind of moving around to see how they look with your stuff like that. If you can't figure out where the numbers go, and you can't get to the calculation part, that's okay. It's more important to get the unit set up properly. You don't want to get in the habit of just kind of randomly multiplying and dividing numbers in your calculator because they show up in the question. That generally doesn't work out so well. If you can just take some time, try to set up the units, try to figure out how you're going to convert from one to another and what that looks like as you write it down. All right, everybody try to set it up. Maybe a little bit. Okay. So I'm going to do it the same way. I start with the number I'm given, and I'm always going to keep the units right along with it. So 145 pounds. And then I'm going to multiply that by a factor that gets me that first step. That first little arrow says I need to go pounds to grams first. That's why we write the green thing first, so we can figure out what our steps are. So we want to go pounds to grams, which means getting rid of pounds and instead having grams. Good so far? Then we go on to our next step. And in fact, if it helps you keep track of it, you can draw a line through the ones that have been canceled out so you can see what you have left. So now we've got grams, and our second part of our plan, or our map, or whatever you want to call that, tells us to go between grams and kilograms. So from grams to kilograms, which means grams is going to be on the bottom, kilograms on top. Once those cancel, then all we're left with is kilograms, which is the answer to the question. All right. So now we fill in the numbers. Remember that the numbers go with their units just like in the equality. So if it says 1 pound equals 455 grams, the 1 goes with the pounds, and the 454 goes with the grams. What about grams and kilograms? We know, well, eventually we'll know that it's 1,000. Where does the 1,000 go? With the grams or the kilograms? The 1,000 goes on top, bottom, the 1 goes on top. So everybody's going to say, yes, you're all right. So the 1,000 goes on top, on the bottom, and the 1 goes on top. And the way that we can remember that is thinking about what that means. So is a gram or a kilogram bigger? You may not have any sense of how big a gram or a kilogram is at this point, but that's part of why we're in this class. Think about when you were in lab last week weighing your crucible. Does anybody remember about how much a crucible weighed? Yeah, so like it was, and that scale was reading in grams, right? So it was maybe 20-ish grams, something like that. Depending on if you had the lid, it could have been different. But anyway, it was way less than 1,000 grams is the point of that, and that was a crucible. So we say that, so we might remember that and say, okay, well, the gram has got to be smaller than the kilogram. So there's got to be 1,000 grams in a kilogram, not 1,000 kilograms. All right, now that that's all set up, we can multiply through by what's on top and divide by what's on the bottom. I would take my calculator here and say 145 times 454 divided by 1,000 is 65.83. So this one didn't come out too crazy, but there's often, like, you do this kind of a problem and there's a whole string of decimal places. So how do you decide where to cut off the decimal places? In this class, the answer is it doesn't really matter. There are rules for it. The chapter 2, I think, has those rules in the beginning of it. We skipped that section, yeah, on how to round off. So we found for this particular class, we're not going to have careful rules about how you round off. So it's kind of up to you. Good rule of thumb is just take about as many significant figures as are in the other numbers in the problem. So we've got like a 145 in the problem, so let's take 3 and call it 65.8. If you called it 65.84 or 0.83, I wouldn't mark you wrong. If you called it 66, I wouldn't mark you wrong either. So it's kind of up to you. If that bothers you and you want to know like the right way to do it, we can talk about it. Come to office hours or something, or read the book, and we can talk about how you're really supposed to do it. But I'm just going to call that 65.8 kilograms. All right. So did you get close? Did you get right on there? Something like that? Okay, good. Got some good nods. If not, that's fine. It's the first time we're doing it. You'll practice and it'll get better. All right. Last thing to say about this before we move on to another problem. If you're solving a problem like this on an exam, it is a really good idea to lay it out like this. The more organized you can put your work on the exam, the more credit I can give you if you happen to make some mistake, like you flip something around or you type it into your calculator wrong or whatever. If you just have a number that you wrote down on the exam, there's nothing I can do about that. If it's wrong, it's wrong. But if you have it all laid out, I can see pretty clearly, oh, everything's right except for this one thing got switched around, and so I can still give you most of the points. So it's always good to organize your work and keep it all there. Okay, let's try one more, and we'll move on to something else. This one says, an athlete has 15% body fat by mass. What is the weight in pounds of the fat in a 74 kilogram athlete? So this has a little bit more to pull out of it. So I'm going to help you with that part and then see if you can set up the rest of the conversion on your own. So let's start looking at it the same way. What units do we start with, and what do we have to end up with? So probably the easiest one, or the most important one to pull out first, is what do you want to end up with? So what kind of a unit do we want to report our answer in? Pounds. And in this one, it's actually important that we be a little bit more specific about that. Pounds of what?
Pounds of body fat.
Yeah, pounds of fat. So the end here is going to be pounds of fat. And what are we starting with at the very beginning of the problem? What number are we given? What is the thing that all these calculations are going to be based on?
74 kilograms.
Right, we're given a couple numbers because we're given the 15% body fat by mass, but it's that 74 kilograms that we want to start with. That's going to give us the best starting place. You actually could solve this starting with the 15%, but it would be a little trickier. So we're going to start with kilograms. Now, is there some number that we can go from kilograms to pounds of fat in this problem? 2.2, but we got to be careful. So let's use that as long as we know it here. So there's 2.2 pounds, or sorry, yeah, that's right, 2.2 pounds in 1 kilogram. So does that mean that we can just multiply 74 by 2.2 and we're done? Not quite. Why not quite? In this case. Yeah, because we only want 15% of that. So if you have that kind of plan in your head and you know how you would do that, go ahead, do that. But let me show you how this works in thinking of it as a conversion of a type. So in thinking of it as a conversion problem, what we would say is that from those kilograms, we're going to get, that's really kilograms of the person. And from kilograms of the person, we're going to get we're going to get pounds of the person. And then pounds of the fat using that 15% idea. You could also do it the opposite way, and you could say kilograms of person to kilograms of fat, and then pounds of fat, and do that conversion second. So what does that look like in a conversion factor? Well, we've got our 2.2 pounds equals 1 kilogram. With that 15%, does anybody know what percent means? Where does that word come from? Out of 100, yeah. Per is like out of, and cent means 100. So 15% means 15 out of 100. So the way that we would use that as a conversion is to say 15 pounds or whatever of fat equals 100 pounds of the person. So every 100 pounds of a person has 15 pounds of fat. So now that we have those two factors, see if we can set this up the same way we did in the previous problem, following the units along.
Test. Are we allowed to use calculators?
Yeah. Yep. You can't use your phone as a calculator on the test, just because you can look stuff up on your phone, but any other calculator. You shouldn't need a graphing calculator or a scientific like just a regular with 4 plus minus multiply divide. We'll have some, I think, too, so if you don't have one, you can use one.
So would the answer be 24.42%?
I don't know. It shouldn't be a percent, because the answer should be in pounds.
Right, 24.42%.
That sounds about right.
Can you just round it off to 24 pounds?
Seems about right. I'm not sure. I'm going to set this up while you're working, finishing up. I would set it up using our plan right here. Call this P for person. So that's how I've got to set up. Calculate it here. We're going to multiply by everything on top, divide by everything on the bottom. So times 2.2 times 15 divided by 100. We get about 24 pounds. Yep.
No, if I do it step by step to know put it all the way across, it's the same.
It's the same thing, yeah. Yeah, so if this idea of having 100 per 100 or 15 per 100 thing seems crazy to you, it's because you are good with percentages and you already know that stuff. So do it however works for you. You never get penalized for doing stuff in a different way that still gets you to the right answer. I just wanted to give people another way to do it that's very follows the same procedure every time kind of a way of doing it. So yeah, if you'd rather do it in steps where you know, oh, I just take the percentage and it's easy, then fine, do it that way. All right, so that's the basic idea of these conversion problems. And we're going to do them this way for all kinds of other stuff. Now, you notice in this problem, this is one example of that. There's a weird conversion factor. Pounds of fat, 15 pounds of fat equals 100 pounds of person. That's not really a true equality. It's more like a ratio, like this many of this per this many of this. So it's weird to write it that way. And so we're going to look at some more examples of that because it actually ends up being useful to think of it less as an equality and more of a ratio with our next idea, which is density. Does anybody know what density is? The what? The mass of an object? Kind of, yeah. It's a ratio between two things. So one of those is mass. Anybody know what another one is? Volume, yeah. So it's a way of expressing how much space a given amount of matter takes up. Or we can say it the opposite way. How much does a given volume of something weigh? Amount of matter or stuff in a given amount of volume or space. So if you have a bunch of things that take up the same amount of space, but they weigh different, then they have different densities. So something that is very dense, how are you gonna experience that? What's something with a high density gonna be like? Yeah, it's gonna feel heavy for its size. So it's gonna feel a lot heavier for how big it is. So if you had a steel ball or something, it would feel a lot better, a lot heavier than like a ping pong ball that is filled with air. Yeah. So that's what we're talking about when we're talking about density. How much mass is in a given amount of stuff? Any matter can have density. So density can apply to solids, it can apply to liquids, and it can apply to gases. It's just how much matter is in a given amount of space. The general way to express this is grams per milliliter. So that's grams over milliliters. Or grams per cubic centimeter. Have you heard of a cubic centimeter or a cc?
Yeah.
So that's the same as a milliliter. It works like this. This is an example of that. So this little cube is exactly 1 centimeter on each side. So if you make a cube that's a centimeter on each side, volume of a cube is the one side multiplied by itself 3 times, so you've got a cubic centimeter. And it turns out that that's the exact same volume as a milliliter. So those two mean the same thing, they're interchangeable. This block is a liter, I believe, which is 1,000 cubic centimeters. Yeah. 1,000. Okay, so why is this important? How do we deal with this? Well, part of its importance is just as a thing that you can measure. So like one of the things we're going to do in lab on Wednesday is to measure the density of different objects and then be able to identify them based on their density, because you could look up different densities and then figure out what you've got. The other way that this is useful is to think of it as a conversion factor. So let's say that we have a particular density. Water's density is 1 gram per milliliter. So sometimes we say the density of water is 1 gram per milliliter. Another way of writing that is 1 gram divided by 1 milliliter. So if you look at it that way, it kind of looks like a conversion factor. You've got a unit on the top and a unit on the bottom. So we can use this in problems to convert between mass and volume. And if you think about it, that's kind of a strange thing because mass and volume are two totally different quantities. So to say that you could convert from grams to milliliters is a little weird because those are different. But if you know the density of something, you can say, well, for the grams of this substance, we can get the volume of this same substance. So let me show you how that works in an example. What is the mass in grams of 150 milliliters of a liquid with a density so there it is, 1.4 grams per milliliter. So this is the kind of thing that comes up in lab, comes up sometimes like in cooking, comes up in medicine, because you don't always have the kind of tool that you need. So in this case, let's say we want to measure something on a balance because it's more convenient. So we want to know the mass, but all we're given is that we need 150 milliliters of the liquid, and we're given the density. We can look up the density. So it's a way to use a mass tool like a balance when we are given a volume tool. And commonly in lab, something we'll do is we do it the opposite way. If you have a liquid, sometimes it's easier to measure that liquid by volume than by mass, because you can use a graduated cylinder or a syringe or whatever. So it makes more sense to do it by volume. So you need the density and you need to be able to do that conversion. So this is what we would do. We would treat it just like those problems we did before. And we would think about this as a conversion problem where we're going from milliliters to grams. So we're given milliliters, we're given 150 milliliters. We want to know how many grams is that. And so we'd set it up like this and go 150 milliliters. And then give ourselves a conversion factor that converted between milliliters and grams. Milliliters on top, we want those to cancel. Now a conversion factor between milliliters and grams, that's not really a conversion factor, that's the density. And the density is given as 1.4. So our last decision then is, where does that 1.4 go? Does it go with the grams or does it go with the milliliters? Yeah, it always goes with the grams. So the first, if it's that inline notation where it's G/ml, the one that's before the slash is on top, and that one goes with the number. So that always goes with the number. So if you see 1.4 grams per milliliter, you should always think about that as 1.4 grams over 1 milliliter. So the number always goes with that first unit that it's right next to. So that means we can put our 1.4 here and 1 down here. And so the mass of that liquid would be 210 grams. No, because the milliliters now have canceled out. So all that's left is grams. Yeah. That's why it's important to follow the units, because it does seem like you should just keep that slash thing on there. Right. So in this case, we're using the density, but we're using it like a conversion. All right. So let's do this. It's about halfway. Let's stop, take a break. If you want to practice this a little bit, the density problems are on page 48 and 49 in your book, and then also in the in all the extra questions in the back of the chapter. So if you want to work on those a little bit while you're getting some food or something, or just take a break, when we come back, we'll talk. We'll get into the next chapter, which is talking about matter and energy. So I'll see you in 15 minutes or so. Let's fit this.